These are the solutions to question number 4 for the 2015 Chaos examination paper. For part A, we have this three-dimensional system of nonlinear differential equations. So V is the number of virus particles, which are also known as virions. X is the population of healthy cells, and Y is the population of infected cells. We're given the parameters here, so we can easily substitute all of that into MATLAB. And we want to determine the number and stability of the fixed points, critical points of this system. For part B, we have a discrete system which models the nonlinear economic duopoly model. So we want to determine fixed points of period 1 and the stability of these fixed points. So for part A, here is our three-dimensional system. To find the critical points, we want to solve dv by dt equals dx by dt equals dy by dt equals 0. So we can use solve command in MATLAB. So we can use the solve command for this. The syntax of this has changed now. You don't need the dits, and remember you put double equals 0, double equals 0, and double equals 0. So you no longer need these dits in the latest version of MATLAB. So we get two critical points at 0, 1, 0, and at this point here. We need to find the Jacobian matrix because we're going to linearize around each critical point. So this is the Jacobian matrix found by simple partial differentiation. Then we substitute for v, x, and y, and here is the Jacobian at the critical point at A. And then we can find the eigenvalues for this using MATLAB. And here are the eigenvalues. Two of these are negative, but importantly, one of them is positive. So overall, this critical point is unstable. For the second critical point, you can see that all of the eigenvalues have negative real part. So they all have negative real part, so this critical point is stable. For part B, we have a two-dimensional discrete system. To find the fixed points of period 1, we want xn plus 1 equals xn, call it x, yn plus 1 equals yn, call it y. So we solve these equations here. So we have this equation, remember, to subtract x here, because we take the x, we subtract x from both sides on this equation. And on this side, we subtract y from both sides. And remember, with the new version of MATLAB, you don't need the dits, and this is double equals 0 and double equals 0. And again, well, in this case, we get two fixed points, which are here. Again, we find the Jacobian matrix, dp dx, dp dy, dq dx, dq dy. We can use MATLAB to find the eigenvalues. Now, in this case, we can see that the modulus of both of these eigenvalues are bigger than 1. The modulus of the eigenvalues is bigger than 1, so this fixed point is unstable. Now, in this case, this first eigenvalue, the modulus, is bigger than 1. So overall, this is going to be unstable. Remember, we have a problem with this one. Lambda 2 is 1. It's neither stable nor unstable. But because one of the eigenvalues here is unstable, overall, this fixed point is unstable. And that concludes the solutions to question number 4.